Hi, in this example we'll study multiplication and consider the number of bits, or precision, of the number, and worry about overflow, which could occur after a multiplication. Let's begin. In this example, we've been asked to create a linear scaling from an 8-bit number n to a 16-bit number m, such that the relationship is 5 times n plus 25 is stored into m. This is typical of an embedded system where we're scaling one number into another. If we were doing this in C, we would define an 8-bit unsigned variable using unsigned char, and the 16-bit unsigned variable used unsigned short, and we'd calculate n times 5 and add 25 and store it back. The compiler would automatically convert or promote n to a 16-bit value, perform a 16-bit multiply, 16-bit add, and store the result. In assembly language, we're going to have to do each step explicitly. Let's begin with the multiply. There are 3 multiply instructions to choose from on the 9s12. Emul is an unsigned 16 by 16 bit into 32-bit product. The emul s is a signed 16 by 16 bit into a 32-bit product. And the mul instruction takes an unsigned 8-bit, multiplies it by another 8-bit to get an unsigned 16-bit product. Because the number 5 and the number n are both 8-bit numbers, we're going to be using the mul instruction because it'll be simpler. The mul instruction takes the 8-bit value in register A, multiplies it by the 8-bit value in register B, and stores the product into register D. So, in order to set up to use the mul instruction, we'll first bring the value of variable n into register A. Notice after the load instruction, register A contains the 8-bit value which was the initial value of n. When we consider overflow in designing software, we will explicitly think about the values in the registers that might happen. In this case, register A might contain 0 to 255. The second step is to bring the constant #5, pound means constant, to bring that into register B. Now, register A has the value from n, and register B has the 5. After executing the mul instruction, register D will contain the value of 5 times n. So again, we'll consider overflow. N is a number from 0 to 255, and when we multiply it times 5, we'll get a value from 0 to 1275. That will easily fit into the 16-bit register D. No overflow can occur. The next step is to add the constant 25. The add D instruction will add a 25 to its original value. So now, register D contains 5 times the value of n plus 25. Once again, considering overflow, register D can now take on the values of 25 to 1300. Notice that no overflow can occur in this addition either. And the last step is to store the result into the variable m. This is a 16-bit store, so we're going to store all of D into m. So, in summary, we looked at multiplication. The 9s12 had 3 instructions. Emul and emul s are both 16 by 16 into 32-bit product. The one we used was the mul, which is an 8-bit by 8-bit into 16-bit product. Again, mul took register A, multiplied it times register B, and stored it into register D. Remember, A and B together really comprise or constitute D. So this is not 3 separate registers. So we either have register D as one 16-bit register, or we consider register A and register B as 2 separate 8-bit registers. Precision is the size or the number of bits. It specifies the range of the numbers. An 8-bit number here in register A can take on the values of 0 to 255. Whereas, after the multiplication, register D is 16 bits and it can take on a value from 0 to 65,535. When designing software, we have to worry about overflow. Overflow occurs when the product or the sum of the operation does not fit back into the register. One way to consider overflow during the design of software is to explicitly write out the range of values that might exist at each of the intermediate steps, and at that point we can decide whether or not an overflow might happen. In this case, the range was small enough such that the output did not overflow. Thank you very much.